Okay, in this unit we are going to be talking about the atomic theory, atoms, what they're made out of, how they were discovered. We're going to do a little bit of history along with it. And so we want to go back to the very beginning, the first time people really started to think about matter. And that takes us all the way back to the ancient scholars. They believed that matter was composed of earth, water, fire, and air, and that you could endlessly divide those things up into smaller and smaller pieces. They didn't really have a good idea of what matter was really made out of. And then we get to a guy named Democritus, and he was really the first person to propose the idea that matter was not infinitely divisible. He said that matter was made up of individual particles. He called them atoms. So that's where our word comes from. Now, Aristotle, who lived at the same time, disagreed with Democritus, and because Aristotle was way more important, his views went unchallenged for 2,000 years until scientists really could find a way to test and actually prove some of Democritus's ideas. So this sums up what each of them thought. Democritus thought that matter is composed of atoms which move through empty space. He thought that atoms were solid, indestructible, and indivisible. So he thought atoms were the smallest things. He said that different kinds of atoms have different sizes and shapes, and that's what determines their properties. Aristotle, on the other hand, thought that empty space couldn't exist and that matter was only made of earth, fire, air, and water. So big difference there between the ideas of those two ancient philosophers. Now that brings us to the early 1800s. From the time of Democritus all the way up to the early 1800s, no one really knew exactly what was going on with matter until John Dalton. And Dalton found a way to really prove what matter is made out of. And he came up with his atomic theory, which says that first, matter is composed of extremely small particles called atoms, just like Democritus. He also said that atoms are indivisible and indestructible, so again, he thought atoms were the smallest things. He said that atoms of a given element are identical in size, mass, and chemical properties. So if you have carbon atoms, every single carbon atom is exactly the same. Atoms of a specific element are different from those of another element. Different atoms combine in simple whole number ratios to form compounds. And we see that. If you think about water, there are 2 hydrogens and 1 oxygen. That's a simple whole number ratio of hydrogen atoms and oxygen combining to make water. And he said, in a chemical reaction, atoms are separated, combined, or rearranged, which really helps us explain the law of conservation of mass. So when we have these chemical reactions, we're not actually creating anything or destroying anything. We're just rearranging how the atoms are bonded with each other. Okay, so let's define the atom. The atom is defined as the smallest particle of an element that retains the properties of that element. So if, what we're going to find out is obviously the atom is not the smallest thing. There are things smaller than atoms. But if you get smaller than an atom, if you talk about subatomic particles, you're not going to have the properties of that particular element anymore. And there is a type of microscope called a scanning tunneling microscope that actually allows individual atoms to be seen. Okay, so let's talk, moving on from Dalton to the discovery of the first subatomic particle. So that came from something called a cathode ray. Okay, so the picture that you see is a cathode ray. And basically what happens is when this glass tube was hooked up to electricity, this glass tube right here was hooked up to a voltage source, as you can see, cathode rays were seen moving from the negative side to the positive side. And basically what was discovered was these rays were made up of negative particles that were eventually called electrons. And a guy named J.J. Thomson was the one that really discovered the electrons. He measured the effects of both magnetic and electric fields on the cathode ray. So he was able to show that the particles in that ray were attracted to the positive side of a magnetic field, so they had a negative charge. And then he was also able to determine the charge to mass ratio. So he was able to figure out that whatever these particles were, they were way smaller than a hydrogen atom, which is the lightest known atom. So he discovered the first subatomic particle. He showed that whatever these things were, they had a charge, and they were smaller than the smallest atom. So they had to be subatomic. They had to be inside the atom, and he called the particles electrons. Now, once Thomson discovered the electron, Robert Millikan used what's called the oil drop apparatus, or the oil drop experiment, to show the charge of an electron. And he basically used an atomizer, and he could manipulate those atoms between the positive and negatively charged plates to figure out how big they were and how much charge was attached to them to know what the charge of an electron was. And he got into some complicated math, which we don't really need to know about. Okay, so now let's think about Thomson's idea. Okay, so he said, all right, first we know there are atoms, and we know that there's something in the atom, and these things, these tiny little things, are negatively charged, right? Well, atoms themselves are neutral, so if matter is neutral, but there are negatively charged things in the atoms, there also has to be positive charge to cancel out the negative charge. Otherwise, matter wouldn't be neutral. So Thomson proposed a model that helped answer this question. He called it the plum pudding model. And he said that an atom is a uniform positively charged sphere containing electrons. And you can see this is the plum pudding model. So he thought, here's an atom, okay, it's this big lump of positively charged material, and the little electrons are stuck in the surface, kind of like raisins in plum pudding. That's why he called it that. All right, so Thomson's model lasted until a guy named Ernest Rutherford proved it wrong. And what Rutherford was doing is he was taking alpha particles, which it's a type of radiation, and he was shooting alpha particles at different metals to see what would happen. So he had a really, really thin sheet of gold foil, and he was shooting these alpha particles at the foil. And so what he expected to happen based on the plum pudding model is he thought that the alpha particles would pretty much go straight through. There might be a little deflection if they get too close to an electron, but they should pretty much just go through the gold foil and come out the other side. Well, here's what happened. Okay, so this is a picture of the apparatus he used. So here's the gold foil. Here are the alpha particles that are coming in, and then this green screen is basically a way of detecting alpha particles. So anytime an alpha particle would hit it, it would light up. So he started shooting the alpha particles, and some of them were going through, some of them were deflected, but then he noticed some of them actually bounced off the gold foil, and that was just an extraordinary thing. If Thomson's model was accurate, there's no way that alpha particles could bounce off anything within the atom. So Rutherford had to change the idea of what an atom was made out of, and he came up with the idea of the nucleus. He said that rather than all that positive charge being spread out, he said that the positive charge and most of the mass is contained in a dense region in the center of the atom, and he called it the nucleus. And then the electrons are held within the atom by their attraction to the nucleus. And so when these alpha particles were coming in, the ones that bounced off were actually hitting the nucleus, and then the rest went through the empty space that makes up the most of the atom and were going through to the other side. Okay, so now we know that atoms are made up of three fundamental subatomic particles. Okay, so we know about the electron from Thomson. We know about the nucleus from Rutherford, and then scientists later on, after Rutherford, figured out that the nucleus wasn't just a hard lump, it was actually made of smaller things called protons and neutrons. So atoms are mostly spherical, they're mostly empty space, and their nucleus is where that mass is. That's where the protons and neutrons are. The electrons are very, very small in comparison to the protons and neutrons in the nucleus. All right, so this kind of summarizes what those subatomic particles look like. The electron will use an E with a little negative to represent electron, P for proton, N for neutron, where they are, what their relative charge is, what their relative mass is. So as you can see, protons and neutrons, they're about the same mass, but electrons are almost 2,000 times smaller than protons and neutrons. So in comparison, electrons really don't add mass to the atom. The mass of an atom comes almost all from the protons and neutrons.